Hi again. This pencast is to look at finite state machines with a data path, also known as Fsmds. What we'll be going through here is a quick catch-up on regular state machines and the difference that an Fsmd exhibits when compared to a normal FSM or finite state machine. And then we will look at a Uart, which is a very good example of a finite state machine with a data path. There's also a lab for you that I'll introduce later, called Lab 5. And the teaching material we are using is in chapter 6 and 7, described here. So I hope you get a chance to read that after you hear these slides. So when we compare an Fsmd with an FSM, again the FSM is a finite state machine we know already. We can say that the FSM as we know it, the finite state machine, when we use that together with the data path, the FSM is used as control logic primarily, or the control path that controls, so to say, the data path. We'll see a schematic in the following slide. And apart from that, we have a number of registers and some operations, we could call it regular operations like a counter or shift register or so, that forms the data path. And by combining regular circuits with an FSM, we can build an Fsmd. An Fsmd can be used to implement an algorithm that could be software previously, to implement that in hardware. It's a good way to distinguish and split it up as a control machine or control path built by the FSM, and then as a number of registers for implementing the actual data processing. Another way of writing that could be to say that we are building a controller that can perform a certain operation on a given data set. That can be done by an Fsmd as well. Here you see a block diagram of an Fsmd, and if we look in the bottom here, we have the control path. The control path is exactly identical to the FSM we have seen before, where we have next state logic, we have a state register, and we have some output logic. The output logic again can be either mealy or more type. What is shown here is a more type output logic, and the only slight difference is that apart from using the outputs directly, we direct some of the outputs as control signals to the top part, the data path. And again, just like we have inputs here called command, we can take status signals from the hardware up in the data path and use that as inputs to the next state logic. Looking up in the top, we have the data path, the part that distinguishes an FSM from an Fsmd. The data path is where the data is being processed. Up in the top, where we could say the controller that handles whatever needs to be done, is in the bottom. And the data path will typically consist of a routing network, like much of our logic will, built from multiplexers or routing components of different kinds. Some functional units that could be multipliers or filters or shift registers or counters or whatever it may be, PWM circuits and so on. And then we typically have some routing network again to determine what happens with the signal. And as always, when we build a synchronous system, we have data registers on the output to register whatever logic operations we have and synchronize them against a common clock. And again, the signal is fed back, and we could exhibit or call this entire block our next state logic, so it looks like the synchronous system we know. A case study of an Fsmd or a practical example could be the Uart that we see here. The Uart is from chapter 7 in the book. This is a block diagram of a complete Uart, and we will dive into the blocks, receiver and transmitter and baud rate generator later on. FIFOs we have already covered. That's basically the FIFOs we have looked at in the previous lab. that can be combined with the Uart. I've tried to highlight the individual parts, the data path and the control path, where I could say all that is highlighted in blue, both for the receiver and transmitter, would be the data path, and that is because we have up here we have the receiver, where we have the serial receiver input, we have the receiver block in the Uart, and as you might know a Uart from your embeds, for instance, a Uart can receive serial data, send across a serial line, or you have probably used USB, but it will be serialized and put into your embed microcontroller, for instance. Once we have received a complete byte or 8 bits of data, the data is assembled into 1 byte. The byte here is sent to the FIFO, so the FIFO can store a number of bytes until the application that may be over here has time to read it. The opposite direction is when we want to write data, then we would have a byte that we can put into the FIFO, if we have the FIFO enabled. The FIFO can then put a byte of data into the Uart transmitter, and the Uart transmitter can send data bytes bit by bit onto the serial line. So this is the data path of the Uart, or the two data paths, where the control part is, or control path, control logic is the rest of the receiver. It's the synchronization part, for instance, generated by the baud rate generator. That's basically just a binary counter that gives a tick once in a while. It synchronizes the receiver and the transmitter so they run the same speed. There is a state machine in here that keeps control over how many bits we have received and if we have according start and stop signals and so on. Same goes for both the FIFOs. We have seen control logic for that in previous chapters and slides, where we have some control logic for the circular buffers in a FIFO. So in that way you could distinguish a functional piece of hardware implemented in VHDL. We couldn't control it or split it into a controller and a data path. Here is an Fsmd chart with the different states of the Uart. I would suggest you pause the video for a while and discuss it with your neighbor, or go through it step by step and figure out what it does, and when we will take a discussion in class and see if we can investigate how it works before we dive into the code. So please spend 5 minutes or so doing this now. So now you have been looking at the Fsmd chart and have an idea of how the Uart works. We will now take a look at one of the functional blocks in the Uart, and this is the receiver, if I remember correctly. What we see here is the register part. The Uart is built completely like any other synchronous system we have seen. Here is just a few more signals. We can see we have state reg, S reg, N reg, and B reg. All of these are assigned their according next values when we have a rising edge clock, and if we have an active reset, all of them will be initialized to 0 and the state reg will be initialized to idle. So this is just like any other synchronous system, and it's just we have some data signals combined into the register process as well. Here we have the next state logic for the receiver, and that looks also like something we have seen before. We just have multiple signals to work with here. We evaluate here what state we are in: idle, start, data, and we'll see a few more on the next slide. And based upon given conditions and start conditions and so on, and what counter values we have, we go to a new state, or we increment a counter, or whatever needs to be done, but that is according to the Fsmd chart we saw just before. So again, spend a minute examining this code and get an idea of what happens, and then we'll move to the next slide. The next slide here shows the remaining part of the next state logic for the Uart receiver. Again, we have the data state here, and we have the stop state here, and in these states we evaluate some counter values and figure out if the entire byte has been received, etc. And again, here we need to have a stop signal to indicate that the transmission has ended, and that can bring us into the idle state again, signaling that we are completely done with the reception. But that should be relatively obvious if you compare it against the ASMD chart. So go back and forth a bit until you can see that they are connected. If you want to find out more, you should look into chapter 6 and 7 in the book. And again, Uarts are part of the next lab we will be working with, so we will definitely dive more into detail.